Welcome back to Talk Tensors, everybody. Today, we're going to be doing a deep dive on a paper that's really gotten us thinking about how we approach time series forecasting with these powerful transformer models that everyone's talking about.
Yeah, time series forecasting, it's like everywhere, right? You need it for so many things, predicting the weather, figuring out how much energy we're going to need, understanding traffic patterns. And these transformer models, they've really become the go-to method for a lot of these tasks.
They really have. But this paper titled Enhancing Time Series Forecasting via Logic-Inspired Regularization kind of throws a wrench in the gears a bit. They basically argue that even though transformers are super effective, they could be even better if they weren't treating all the relationships they learn in the data as equally important.
And it's true, right? If you think about it, the way these models work, they chop up the time series data, like stock prices or temperature readings over time, into these little chunks, what they call tokens in the paper. And then they use this thing called self-attention to figure out how all those tokens are connected to make a prediction about what comes next.
Right. It's like they're learning that, say, if there's a big spike in temperature, maybe that means there's going to be a jump in electricity demand a few hours later.
Exactly. But the thing is, existing transformer methods basically treat all these learned relationships, these token dependencies, as they call them, the same way when they're making their predictions. But what the authors of this paper are saying is that's not necessarily the best way to do it. What if some of those relationships are actually more important than others, depending on what you're trying to forecast? A connection that's really crucial for predicting something way off in the future might not matter at all, or even mess things up when you're just trying to predict the very next data point.
And they actually have some really interesting evidence to back that up. They ran this, what they call a toy experiment, with real-world data sets on electricity consumption, weather patterns, and traffic flow. They basically took two pretty popular transformer models, ITransformer and Patch TST, and started messing around with the dependencies. Like they would remove some of them and see what happened.
Yeah, and the results were pretty wild. They found that if you got rid of a specific dependency, it could actually make the short-term forecast more accurate, but then it would make the long-term forecast way worse.
Or the other way around.
Right.
Right. So basically what they're saying is that a dependency that's super important for predicting something in the far future might actually be useless or even harmful for predicting the very next step. So we need to be a little more strategic about which dependencies we're using.
Exactly. So the big questions this paper tries to answer are, one, what makes a token dependency actually effective? And two, how can we make models that learn to focus on those effective dependencies and ignore the ones that are just adding noise or whatever? And the really cool thing is they actually turn to logic, like formal logic, for inspiration.
Logic. That's not something you hear every day in the world of machine learning. So how do they even begin to connect those two things?
It's actually pretty neat. They build this whole logical framework specifically for time series forecasting, which they call LTSF. And they basically draw these parallels between how a transformer model works and like the basic elements of logic. So think of it like this. The possible situations in logic are like all the different real-world time series data sets you could have. The way the transformer processes the data creates these formulas which represent the past data. And then the meaning function is how the model translates those representations into predictions.
And the validity is basically how accurate those predictions are in different situations.
Right. And they use this framework to define what makes a token dependency effective. And this is where it gets really clever. They borrow this concept from logic called an atomic formula.
Okay, I think I vaguely remember that from my philosophy classes way back when. Refresh my memory.
Yeah, so imagine you're trying to describe a shape, like a square or a circle. You need these basic elements, these atomic formulas that you can't really break down any further without losing the meaning of what you're describing. It's like the simplest, most essential building blocks of the description.
Okay, I get it. So they're saying that effective token dependencies are the ones that help the model create those atomic formulas as its internal representations of the time series. It's like they're capturing the essence of what needs to be predicted.
Precisely. And they argue that if you lose any part of that atomic information, your prediction is going to suffer. So the goal is to train the transformer to produce these fundamental unbreakable tokens, but only using the dependencies that actually contribute to that core meaning. But the question is, how do you actually make a neural network do that?
Right. Because neural networks aren't exactly known for their logical reasoning skills.
That's where their new method comes in. It's called attention logic regularization, or Atn-L Reg. And what's cool is it can be plugged into pretty much any transformer model for time series forecasting.
So what does it actually do? How does it make the model more logical?
They noticed that there's an interesting analogy between how a transformer learns and how you might break down a complex logical statement into its simplest, most essential parts. First, you kind of decompose the input, like taking a long sentence and separating it into individual words or phrases. Then you combine those parts into new expressions, kind of like forming clauses. And finally, you make sure those expressions are as concise and self-contained as possible so the meaning is clear.
Okay, so you're saying that standard transformers are good at the first two steps, breaking down the input into tokens and then using attention to combine them. But they're missing that last step, making sure the representations are as minimal as possible.
Right. They tend to use all the dependencies they learn, even if some are redundant or not really needed for a particular prediction. So Atn-L Reg acts as a filter to encourage the attention maps, which represent the token dependencies, to become sparse.
Sparse, what does that mean exactly?
It means they have a lot of zeros in them. So instead of having strong connections between every single token, the model is forced to be more selective about which relationships it pays attention to. And it does this using a technique called L1 regularization. Think of it like this. You have a recipe with a ton of ingredients, but only a few of them are really essential for the flavor you want. L1 regularization is like a chef who carefully reduces the amounts of the less crucial ingredients so those key flavors can really shine through.
Okay, so by making the attention map sparse, you're basically telling the model, hey, focus on the relationships that really matter. But how do you ensure that it's actually picking the right relationships, the ones that are actually leading to those atomic representations?
It's all about the model's main goal, making accurate predictions. Remember, the model is still being trained to minimize the prediction error. Atn-L Reg just adds this little penalty for using more dependencies. So it has to balance these two objectives, making good predictions while being as efficient as possible with the dependencies it uses. And the idea is that it will naturally get rid of the less effective dependencies because they don't really help it predict better, but they do cost it something.
I like that analogy. It makes it easier to grasp. So they're not telling the model exactly which dependencies to use. They're just kind of nudging it in the right direction. Did they have any mathematical proof that this whole approach actually makes sense?
Yeah, they actually did this whole theoretical analysis where they came up with a generalization bound for transformer-based time series forecasting. And basically what that means is they have a way of mathematically estimating how well a model trained on a specific data set is going to perform on completely new data that it's never seen before. And they show that when you apply this L1 regularization to the attention map, like Atn-L Reg does, you can actually make that bound tighter.
So what does that mean in a practical sense?
It means the model is less likely to overfit to the data it was trained on, so it should perform more consistently on new data. It's like it's learning the underlying patterns better instead of just memorizing the training example.
Right, that makes sense. But theory is one thing. Did they actually test this on real-world data? Did Atn-L Reg really improve the forecasting accuracy?
Oh, yeah. They did a whole bunch of experiments. They took two strong transformer models, ITransformer and Patch TST, and added Atn-L Reg to them. Then they tested them on 6 different real-world data sets. These data sets were all about different things like electricity consumption, weather patterns, traffic flow, and solar energy production. And they compared how those enhanced models performed against 9 other state-of-the-art time series forecasting methods.
So what was the verdict? Did Atn-L Reg live up to the hype?
Pretty much. The iTransformer model with Atn-L Reg consistently had the best average performance across all 6 datasets. Patch TST also saw some improvement, but it wasn't as dramatic. They think that might be because of the way Patch TST breaks down the input data into fewer tokens to begin with. But they did see a really big jump in performance on the traffic dataset, which has a ton of input tokens and therefore a lot of potential dependencies. So that supports their idea that this method is especially effective when you have a lot of relationships to sift through.
Right, because that's where the potential for redundancy is highest.
Yeah.
And they also actually measured how sparse the attention maps became with Atn-L Reg, right?
Yep. They compared the original iTransformer to the version with Atn-L Reg and looked at how many of the attention scores were basically 0. And the results showed that Atn-L Reg led to much sparser attention maps. So the model was using far fewer dependencies to make its predictions, but it was still getting better results. They even visualized those redundant dependencies that the original model was using, but were pruned away by Atn-L Reg, and you could clearly see the reduction.
So just to sum it all up, this paper basically says, hey, transformers are great, but they can be even better if they're a bit more picky about the relationships they focus on. They brought in this whole logical perspective to define what makes a dependency truly important, those atomic formulas that capture the essence of what needs to be predicted. And then they created this really neat technique, Atn-L Reg, that encourages models to use a smaller set of those more effective dependencies, which not only has some theoretical backing, but also leads to some real-world performance gains.
Exactly. And what's really exciting is that it's such a flexible approach. It can potentially be used with a whole range of different transformer models, opening up a lot of possibilities.
Absolutely. All right, time for our novel notions segment, where we try to push the boundaries a little bit and think about what new research directions this paper could inspire. So what are your thoughts? Where can we go from here?
Well, one thought I had was, what if we could make the definition of those atomic formulas more dynamic? Like in this paper, it's kind of fixed based on this idea of indivisibility, but what if the model could actually learn what makes a piece of information indivisible based on the specific forecasting task it's trying to solve, or even based on what stage of training it's in?
So instead of having a fixed definition of atomic, it could kind of evolve over time as the model learns more. That's a really interesting idea, almost like a model that's self-aware of what's important in the data.
Exactly. It could be like a meta-learning situation where the model is actually learning how to learn those evolving definitions of atomic. And maybe we could even draw some inspiration from how humans develop a deeper understanding of complex systems over time. Like when we're first learning about something, we might focus on the really basic building blocks, but as we get more experience, we start to see those bigger picture patterns. Maybe we could get models to do something similar.
That's a really cool thought. What else comes to mind?
Well, since Atn-L Reg leads to these sparse attention maps, I think there's a huge opportunity to explore the interpretability benefits. I mean, the paper already showed that the model learns to rely on fewer dependencies, but could we take that a step further and actually interpret those remaining important dependencies as meaningful relationships within the time series?
Right. Because if we know which dependencies are important, we might be able to understand why the model is making certain predictions, not just what those predictions are.
Exactly. And that would be super valuable in a lot of real-world applications. Like, imagine you're using this to predict anomalies in a complex industrial process. If the attention map is really sparse, it might reveal that only a handful of sensor readings at specific times are actually crucial for predicting that anomaly. And if you can visualize and understand those patterns, it could give you a much deeper understanding of how the system works.
It could be like having a map that tells you exactly which past events are the most likely to cause problems in the future.
Yeah, and that kind of insight could be huge for things like preventative maintenance or risk management. And it also ties into this whole push for explainable AI, where we want to be able to trust our models, not just because they make good predictions, but because we can actually understand the reasoning behind those predictions.
Absolutely. Those are some really fascinating possibilities. It's amazing to think about how bringing in ideas from a seemingly unrelated field like logic could lead to such practical and impactful advances in machine learning.
For sure. And just to be clear, these are just some initial thoughts, just spitballing here. But I think there's a lot of potential in these directions.
Absolutely. All right, so if you want to get into the nitty-gritty details of this paper, the logical framework, the mathematical proofs, all that good stuff, we've got a link to the paper in the show notes. Go check it out. It's
a really well-written paper, and they explain everything really clearly, even the more technical stuff.
And before we wrap up, just a thought-provoking question for our listeners. This paper showed how logic can offer a new way of understanding how deep learning models work. So, what other seemingly unrelated fields might hold the key to future breakthroughs in AI? It's something to think about.
Yeah, it's a wide open field. Who knows what we'll discover next? It's an exciting time to be working in this area.
It really is. Thanks for joining us for this deep dive, everyone. We'll catch you next time on Talk Tensors.